Alright, in today's video we want to cover exponential growth. So we've learned how to analytically solve a differential equation using the separation of variables method. So we have a solution. We know how to solve general differential equations from the first video of this unit. We know how to approximate them with Euler's method. And now we know how to analytically solve some through the method of separation of variables. And we're going to learn some more methods for first order equations in the next video, but now we're going to apply what we learned in the separable equations to a couple of word problems that really have to do with exponential growth. So this is really important for modeling population size. And actually, in biology, if you take AP Biology, you'll recognize this. Even though it's not advertised as a calculus-based course, you see differential equations there just because of how vital it is to modeling ecological systems. So today we're going to be talking about exponential growth. Let's get started. So let's go through a couple definitions before we do any problems. So we have the law of exponential growth, and that says that the rate of how a population grows is proportional to the population at that time. So dp dt equals kp. And then we also have an initial value problem where p of 0 is equal to p naught. So that sets our y-intercept on a graph of p versus t. So if we have p here and we have t there, we're going to have some initial p naught, and that can go up, that can go down, whatever we set it to. But if our derivative is proportional to our initial population, that means we're dealing with a natural exponential. So we're going to get an exponential curve like that. And thus solving the differential equation, we can, with a general solution, we determine that our population at any time t is going to be the initial population times e to some constant kt. Okay, so now we also have something called logistic growth. So there's usually some constraint that we have. Populations don't grow infinitely. Usually what's going to happen is they're going to grow, it's going to look like they're growing exponentially for a while, and then they're going to kind of level off. It's kind of what we hope happens with the COVID pandemic. The COVID cases, we hope they level off, right? Because it would be unreasonable to assume that they go infinite. We don't have infinite people on this earth. So we won't get infinite COVID cases, just like we won't get like an infinite population of rabbits. That would be unreasonable. So we use logistic growth when we have a constraint to say that, hey, we have some sort of carrying capacity that we need to account for so that our population doesn't grow to become infinite. So let's look at the formula for logistic growth. That says that the derivative, the rate of population growth with respect to time, so dp dt is equal to k times p times 1 minus the population over some carrying capacity m. So this is some carrying capacity that says, hey, we can't be infinite here. Okay, so now let's look at some problems. Let's look at an example here. This isn't going to be logistic. This is normal exponential. Let's say that we have a bacteria culture. The bacteria grows at a rate of 3,000 times e to the 2/5 t. And our initial population is 7,500. Find the population at t equals 5. I didn't assign units here, but let's assume this is hours or something. So we can make our graph, and we'll have population here, we'll have time there, and we're going to start at 3,000, right? And we're going to look like a natural exponential with some sort of prefactor there, so that we know we're growing with respect to some k. So 2/5 would be equal to k. So you might remember from pre-calculus, sometimes you might be solving for k, but now we're going to be solving for an actual population, something that we really haven't been able to do without our normal population function. So we have the rate, we don't have the population. So this is dp dt, this is not p of t. So let's try to solve this equation. So dp dt is equal to 3,000 times e to the 2/5 t. Okay, so let's change this p to the amount of bacteria So we're going to make this dB instead of P. So we get that dB, we're going to multiply by dt, and that's going to separate everything. So we're just going to get dB, so we'll make that a B because we want bacteria, maybe not population. dB is equal to 3,000 times e to the 2/5 t. Now we're going to integrate, and that's going to give us our function of B. So we get the integral of dB is equal to 3,000 times e to the 2/5 t. Okay, so now we are going to integrate this, which means multiplying by 5/2, and this is going to give us b of t equals 7,500 times e to the 2/5 t. Great, that agrees with our population, initial population. So now we're going to plug in b of 5. It's going to give us 7,500 times e squared, and that is going to be equal to 55,418 bacteria. So you can imagine how fast that actually grows. You start out with 7,500, then you end up with 55,000 in a matter of 5 units of time. That's pretty incredible. Of course, this unit of time might be years, in which case maybe it's not growing so fast. But anyways, that's an example, pretty normal example for this sort of problem. As long as you can integrate those, you're really going to end up fine, and as long as you can recognize what values you're starting with. All right, let's do another one. So this is going to be kind of a more abstract problem. We're going to be dealing with more of a literal equation. So we want to find the solution to the logistic model. So the logistic model, as we saw earlier, the law says dp dt is equal to kp times 1 minus p over m. Okay, so as you can see, we can apply similar separable equation analytic solutions to this guy, but it's going to be a little bit more involved just because we've got that argument inside of the parentheses. That might be a little bit trickier to deal with. So we are going to manipulate this so we get all of the p's on one side, and then we'll get the k dt on the other side. So we get dp over p minus, or dp over p times 1 minus p over m is equal to k dt. And then we're going to integrate both sides. So we get integral dp over p times 1 minus p over m equals integral k dt. Now this integral looks a bit more tricky, so we are going to need to manipulate this guy so that we can solve it. So we are going to get 1 over p times 1 minus p over m. We're gonna manipulate this so we get m over p minus p over m. And then what we're going to do is we're going to apply the method of partial fractions to separate this into two fractions. I'm not going to go through how we do that because we did that in section, we did that back in like video 70, 74 or something like that. So we are going to separate that to partial fractions. The coefficients are 1 and 1. We get 1 over p plus 1 over m minus p. You can easily integrate both of these, both natural log integrals actually. You get integral 1 over p plus 1 over m minus p dp is equal to integral k dt. And obviously this is easy to solve. We get natural log absolute value p minus natural log absolute value of m minus p is equal to kt plus c. We got to remember the integration constant. Okay, we can apply logarithm properties, multiply everything by -1. We get natural logarithm of m minus p over p is equal to negative kt minus c. Now we can exponentiate both sides and apply exponentiation rules. We get a natural or absolute value of m minus p over p is equal to exponential of negative kt minus c. We're going to let a equal the constraint minus the initial condition over the initial condition. Once we do this, we get m minus p over p is equal to a times e to the negative kt. Solving for p, we get the population as a function of time is equal to m over 1 plus a e to the negative kt, and that, of course, is our solution to the logistic model for differential equations. All right, so this kind of wraps up 3 videos on separable differential equations. In the next video, we're going to talk about linear equations and integrating factors. We'll cover that a little bit. We might do some integral equations as well. And then we're going to cover some like differential systems, like ecological models. And then we will be moving off to the world of infinite sequences and series. We'll see you guys then. Bye.